Tonight, we're going to look at something that surrounds you right now. Not a theory, not a future prediction, not something astronomers are worried might happen one day. Something that is already true, already verified, and already being measured by some of the most sensitive instruments ever built. The space you are sitting in, the street outside, the city, the continent, the planet, the solar system, all of it is inside a hole. Not a black hole, not a collapse. Something older and quieter than that. Cosmologists call it the local void. And the reason no one told you about it is not that it was hidden, it is that what it implies about where we are, how we move, and what is pulling at everything around us is the kind of information that takes a while to fully arrive. By the end of tonight, you will understand what a cosmic void actually is, why being inside one changes the story of the universe you thought you lived in, what is pulling our entire galaxy at hundreds of kilometers per second, and why the map of the cosmos that most people carry in their heads has always had a gap in it. Before we get started, if this kind of deep space content is what you come here for, take a moment to subscribe or leave a like. It genuinely helps this channel reach more people who want to think about these things. Now, let us begin. Start with something simple. Look at the night sky on a clear night, away from city lights, and the first thing you notice is not emptiness. It is fullness. Stars everywhere. The pale band of the Milky Way arching across the sky. Points of light so dense in some directions that they blur into a soft glow. The sky looks full. This is the first illusion. And it is a good one. The human eye is a short-range instrument. It sees what is close, and it draws conclusions about what is far. When you look at the Milky Way, you are seeing the combined light of hundreds of billions of stars compressed into one visible band by the limits of your visual field. The sky looks full because the stars in our galaxy are close enough, relative to the distances involved, to be visible. You are not seeing the universe. You are seeing the inside of your own neighborhood, projected on the dome of the sky. The nearest star beyond the Sun is Proxima Centauri, roughly 4.2 light-years away. Light from Proxima Centauri takes 4.2 years to reach your eye. Every star visible to the naked eye in the night sky is within a few thousand light-years of Earth. A few thousand light-years is a small distance, even by galactic standards. The Milky Way is roughly 100,000 light-years across. The stars you can see cover perhaps a few % of the galaxy's diameter in any direction. What this means is that the night sky, as full as it looks, is showing you a tiny local sample. A neighborhood, a few thousand light-years of stars arranged in the patterns and constellations that human culture has been reading meaning into for tens of thousands of years. Step back from that neighborhood, even slightly, in the mental sense of zooming out, and the picture changes immediately. If you could somehow rise above the Milky Way and look down at the local universe from a distance of a few 100 million light-years, what you would see is not a uniform distribution of stars and galaxies. You would see structure, enormous filaments of galaxies stretching across space, connected at nodes where superclusters pile up, with vast regions between them that contain almost nothing at all. Those regions of almost nothing are called cosmic voids. They are not rare. They are not the exceptions in the large-scale structure of the universe. They are in fact the majority of the universe by volume. Most of the space in the observable cosmos is void. The filaments and walls and superclusters, all the galaxies and all the light and all the matter, occupy only a relatively thin fraction of total cosmic volume. The rest is the deep between. estimates suggest that cosmic voids account for somewhere between 70 and 80% of the universe's total volume. The matter that humanity has ever observed, every galaxy ever photographed, every cluster ever mapped, every filament ever traced, exists inside roughly 20 to 30% of the available space. The majority of space in the universe is very nearly empty. This means that when you look at images of the cosmic web, images produced by large galaxy surveys or computer simulations of the universe's large-scale structure, the visual impression they give is somewhat misleading. The images show galaxies and filaments and clusters because those are the luminous things, the things the surveys can detect. The voids are the dark spaces between, and in a visual representation, the dark spaces between are easy to read as background, as nothing, as the canvas the structure is drawn on. But the voids are not background, they are the majority. The filaments and clusters, which dominate visually because they are bright and complex and have structure, are actually the minority of the universe's volume. The universe's volume is mostly void. The structure is the exception, not the rule. The cosmic web, beautiful as it looks in those images, is actually a thin lace of matter stretched across an ocean of near emptiness. And the question that cosmologists have been piecing together over the past few decades is a surprisingly uncomfortable one. Where exactly are we in that structure? And the answer, which has been assembled piece by piece from galaxy surveys and peculiar velocity maps and CMB measurements and gravitational flow analysis, is that we are in the ocean. We are in the near emptiness. We are inside the majority. The answer that has emerged from the data, piece by piece, is that we are not on the edge of a filament. We are not at a node. We are not near the dense interior of a supercluster. We are inside a void, not at the edge of one. Inside one. This is what no one told you, and understanding it requires going back to some things you thought you already knew. Before you can understand the whole, you have to understand what fills the space around it. The large-scale structure of the universe is one of the most counterintuitive things cosmologists have discovered about the cosmos. It looks at large enough scales, nothing like the roughly uniform distribution of galaxies that early astronomers assumed. It looks like a web. This cosmic web, as it is often called, is a three-dimensional structure built from dark matter and the galaxies that trace its shape. Dark matter, matter that does not emit or reflect light, but has mass and therefore gravity, is distributed across the universe in a specific pattern driven by tiny fluctuations in the early universe. Those fluctuations grew over billions of years as gravity pulled matter toward the denser regions and away from the emptier ones. Think of it this way. The early universe was not perfectly smooth. There were tiny density variations, regions where the matter was slightly denser than average, and regions where it was slightly less dense. These variations were small, less than 1 part in 100,000, but they were real. Gravity is patient. Over hundreds of millions of years, the slightly denser regions attracted more matter from their surroundings, becoming denser still. The slightly underdense regions lost matter to their neighbours, becoming emptier still. The process amplified the initial tiny differences. Small density contrasts became large ones. Regions that started slightly above average density became galaxy clusters. Regions that started slightly below average density became voids. The universe sorted itself under gravity's influence into the structured web of filaments and emptiness that surveys have been mapping for the past few decades. This structure was first clearly seen in the Centre for Astrophysics Redshift Survey in the 1980s, when Margaret Geller and John Huchra produced the first large-scale maps showing galaxies arranged in sheets and filaments surrounding large empty regions. What the maps showed was not a random scattering of galaxies. It was a structure, a pattern, a web. The result is a cosmos organized into filaments, sheets, and walls of matter, the densest of which become the galaxy clusters and superclusters we can observe. Between those filaments and walls are the voids, enormous regions where matter has been drawn out by the gravity of the surrounding structure, leaving behind a space that is not quite empty. There are some stray galaxies even in voids, but the region contains far less matter per unit volume than the regions around it. To give you a sense of the scale, a typical cosmic void is somewhere between 100 and 400 million light-years across. The observable universe is roughly 93 billion light-years in diameter, so a single void can span nearly 0.5% of the full observable universe in one direction. These are not small gaps, they are not background features, they are the dominant feature of the universe's architecture. Here is the thing about living inside a void that matters most immediately. If you are inside a void and you look outward toward the wall of the void, which is where the surrounding filaments and superclusters are, you are looking at regions of higher density than where you are. And regions of higher density have more gravity. That gravitational pull, operating across hundreds of millions of light years, exerts a force on everything inside the void, including us, including the Milky Way, including every galaxy in our local neighborhood. The void is pulling everything inside it toward its walls. Not dramatically, not quickly by any human standard, but measurably. Persistently, with the patience of gravity operating over billions of years. We are not sitting still inside our hole. We are being pushed out of it. The idea that the Earth moves through space is not a new one. We know the Earth orbits the Sun. We know the Sun orbits the center of the Milky Way. We know the Milky Way is in motion relative to other galaxies. But there is a motion that most people never hear about. A motion that sits on top of all those other motions, a drift that is not caused by any single nearby body, but by the gravitational architecture of the large-scale universe itself. And it took decades of careful measurement to find it. It started with the cosmic microwave background. The cosmic microwave background is the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was a hot, dense plasma in which photons, particles of light, could not travel freely. Every time a photon tried to move, it immediately collided with a charged particle and was scattered in a new direction. The universe was opaque. When the plasma cooled enough for neutral atoms to form, the universe suddenly became transparent. The photons that had been trapped in the plasma were released and began traveling freely in all directions. Those photons are the CMB. They have been traveling through the expanding universe for roughly 13.8 billion years, and they arrive at Earth today from every direction, carrying information about the state of the universe when they were released. The expansion of the universe has stretched their wavelength dramatically. They began as visible and infrared light and have been redshifted all the way into the microwave portion of the spectrum. They arrive at a temperature of about 2.7 degrees above absolute zero. They are extraordinarily cold, which is why they require microwave instruments rather than ordinary telescopes to detect. The CMB is extraordinarily uniform. In all directions to extraordinary precision, it has nearly the same temperature. The small variations in temperature, the tiny fluctuations, are the imprints of the density variations in the early universe that eventually became the large-scale structure we see today. Mapping those fluctuations precisely is one of the major achievements of modern cosmology. The fluctuations in the CMB are tiny, roughly 1 part in 100,000 relative to the background temperature. But those tiny fluctuations carry enormous information. Their statistical properties, the distribution of sizes and amplitudes of the hot and cold spots, encode the composition of the early universe, the amount of ordinary matter, dark matter and dark energy, the geometry of space, and the initial conditions that seeded the cosmic web. The entire project of modern cosmology, measuring those small temperature differences with increasing precision, is reading the imprints of the universe's infancy on the oldest light we can detect. But there is one feature of the CMB that is not a fluctuation. It is a pattern. In one half of the sky, the CMB is very slightly warmer than average. In the opposite half of the sky, it is very slightly cooler. The temperature difference is small, about 0.1%, but it is consistent across the full sky, and it is perfectly smooth, not a fluctuation pattern, just a steady gradient from one side of the sky to the other. This pattern is called the CMB dipole, and what it means is that we are moving through the CMB. The half of the sky that appears warmer is the direction we are moving toward. The cooler half is the direction we are moving away from. The Doppler effect shifts the apparent temperature of the CMB slightly warmer in the direction of motion and cooler in the opposite direction, exactly like how the sound of a passing train is higher in pitch as it approaches and lower as it moves away. We are moving at roughly 370 kilometers per second relative to the CMB. For comparison, the speed of light is about 300,000 kilometers per second. So 370 is not relativistic, not even close. But it is not slow by any earthly standard. 370 kilometers per second is more than 1,000,000 kilometers per hour. Earth orbits the Sun at about 30 kilometers per second. The Milky Way rotates and carries the Sun around its center at about 220 kilometers per second. All of those motions are layered, but the total motion of our galaxy through the CMB reference frame comes out to roughly 370 kilometers per second. If you could travel at that speed, you could cross the diameter of Earth in about 35 seconds. You could circle the Sun in roughly 25 hours. You could reach the Moon from Earth in a little under 20 minutes. The Milky Way, the entire galaxy, along with everything inside it, is moving at over 1,000,000 kilometers per hour through the ancient radiation field of the early universe. The next question was obvious. What is pulling us? Astronomers knew the Milky Way was in motion long before they understood why. The velocity was measured, the direction was mapped. What was missing was a clear physical cause. In the 1980s and 1990s, researchers started to identify candidates. The Virgo cluster, the nearest large concentration of galaxies, is about 65 million light-years away and contains thousands of galaxies. Its gravity pulls on the local group, which is our small cluster of galaxies including the Milky Way and Andromeda. That pull was measurable. 65 million light-years is a long way. To put it in perspective, the light reaching us from the Virgo cluster right now left those galaxies 65 million years ago, around the time the last non-avian dinosaurs were going extinct on Earth. The gravity from those galaxies travels at the same speed as light. It propagates outward as changes in the gravitational field, and those changes also move at light speed. What we are feeling from the Virgo cluster right now is the gravitational effect of its mass configuration 65 million years ago. But when researchers added up the contribution from Virgo and the other nearby concentrations they knew about, the numbers did not match the observed velocity. Something else was pulling. Something bigger, further away, and not yet fully mapped. In the mid-1980s, a team of astronomers called the Seven Samurai, researchers Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner were studying the peculiar velocities of elliptical galaxies to measure the cosmic flow. Peculiar velocity is the term astronomers use for the component of a galaxy's motion that is not explained by the overall expansion of the universe. In an expanding universe, distant galaxies recede from us simply because space is stretching. But on top of that expansion, galaxies have additional motions caused by local gravitational influences. Those additional motions are the peculiar velocities. The Seven Samurai found a coherent pattern. Many galaxies across an enormous volume of space were all flowing in roughly the same direction, a bulk motion that went beyond what nearby gravity sources could explain. They called the center of this flow the Great Attractor, and they placed it in the direction of the constellation Centaurus, somewhere between 150 and 250 million light-years away. The Great Attractor is real. There is a genuine concentration of mass in that direction, centered on the Norma cluster and the broader Norma supercluster. This mass is large enough to have a measurable gravitational effect on hundreds of millions of light-years of surrounding space. But once again, when researchers added up the Great Attractor's contribution to the observed cosmic flow, it still did not fully account for the measured velocity. There had to be something even larger. In the early 2010s, a new study led by Brent Tully of the University of Hawaii and a team of collaborators produced the most detailed map of cosmic flows ever made. They mapped the peculiar velocities of thousands of galaxies across hundreds of millions of light-years and used that data to trace the gravitational watersheds of the local universe. They discovered something that had been lurking in the data for years without being fully recognized. The flows did not just converge on the Great Attractor, they converged on something larger still. A supercluster so immense that it had not been recognized as a single structure because much of its mass was behind the plane of the Milky Way, obscured by our own galaxy's dust and gas and stars, hidden in what astronomers call the zone of avoidance. The zone of avoidance is simply the region of sky where the Milky Way's own disk blocks our view of what lies beyond, a band across the sky where background galaxies become impossible to observe at optical wavelengths because of intervening dust and bright foreground stars. The Shapley concentration, a massive supercluster beyond the Great Attractor, at a distance of roughly 650 million light-years, was also contributing significantly to the local flow. Both the Great Attractor and Shapley were pulling the local universe toward them. The combined picture that emerged from the flow analysis was of a structure vastly larger than anything previously recognized as a single coherent gravitational unit. They named it Laniakea. Laniakea is the name given to the supercluster that the Milky Way belongs to. In Hawaiian, Laniakea means immeasurable heaven. The name is appropriate, and it was chosen deliberately. The research team included researchers of Hawaiian heritage, and the name honors both the scale of the structure and the cultural tradition of navigation and observation that Hawaii has a long history with. Laniakea is not defined the way earlier superclusters were defined, by proximity or clustering. It was defined for the first time by gravitational flow. Tully and his colleagues redrew the boundaries of the local cosmic structure by asking a simple but powerful question. Which galaxies are flowing toward the same point? Galaxies that share the same attractor, that are being pulled toward the same gravitational center, are part of the same structure, regardless of how far apart they are from each other. This is a profound shift in how superclusters are understood. Under the old definition, a supercluster was simply a region where galaxies were denser than average, with boundaries defined somewhat arbitrarily by where the density fell to a chosen threshold. Different researchers drew the boundaries differently, and the resulting catalogues of superclusters were inconsistent and fuzzy. Under the flow-based definition, a supercluster is a gravitational watershed, a basin within which all matter flows toward the same centre. The boundaries are defined physically by where the gravitational flow changes direction, and they have a precise meaning. The two definitions give different answers for the boundaries and sizes of local superclusters, and the flow-based definition generally gives larger, more coherent structures. The Virgo supercluster, which had been identified as our local supercluster under the older density-based definition, is, under the new flow-based definition, just one region within the larger Laniakea structure. The Virgo supercluster is not a complete supercluster. It is a lobe of Laniakea, the region closest to the Virgo cluster. The boundaries of the structure we belong to are much larger than previously recognized. Using this definition, Tully's team mapped a supercluster containing roughly 100,000 galaxies, spanning about 520 million light-years, and containing a total mass of roughly 100 million billion times the mass of the Sun. The visualization they produced, a three-dimensional map of the galaxy flows inside Laniakea, shows streams of galaxies moving like rivers flowing toward the same sea, all converging toward the Great Attractor region at the center. The visualization, published along with the 2014 paper in the journal Nature, was widely shared and discussed when it appeared. For many people, it was the first visual representation of Laniakea that made the structure legible, not as a list of galaxy coordinates, but as a flowing, dynamic structure with a clear center of attraction and clear edges where the flow changed direction. The Milky Way appears as a tiny dot near the edge of one of the filamentary streams, undistinguished in size, flowing slowly toward the center along with everything else in the watershed. This is the supercluster we live in. And we do not live in the middle of it, we live near the edge. The center of Laniakea, the gravitational attractor toward which the entire supercluster is flowing, is in the direction of the Great Attractor, the concentration of mass that the Seven Samurai identified in the 1980s. From our position near the edge of Laniakea, everything in the supercluster, including the Milky Way, is being pulled toward that center. But here is the complication that the void introduces. The Milky Way is not only being pulled toward the center of Laniakea by the gravity of Laniakea's mass, it is also being pushed, not by a physical force in the ordinary sense, but by the relative underdensity of the local void. The void we live inside has less matter than the universe's average. That means it has less gravity than the surrounding regions. And when you are inside a region with less gravity than its surroundings, the surrounding regions pull you toward them. You drift toward the denser walls, toward the filaments and clusters that form the edge of the void. The void is, in the language of gravitational dynamics, repelling you, not through any exotic force, but simply because it has less gravitational pull than everywhere else, and you therefore accelerate away from it toward the regions that do have stronger pull. The push from the void and the pull from Laniakea's attractor happen to point in roughly the same direction. The Milky Way is being drawn toward the same destination by two separate mechanisms. The void is expelling us toward the wall. The supercluster is pulling us toward its center. They cooperate. A 2017 study led by Yehuda Hoffman and collaborators used galaxy flow data to separate the contributions of overdense attractors and underdense voids to the local cosmic motion, and found that the local void contributes a repulsive component to our velocity that is comparable in magnitude to the attractive pull of Laniakea. In other words, the void is pushing us roughly as hard as the attractor is pulling us, and both forces are pointed in the same direction. This is why the local cosmic flow is as strong as it is. We are not being moved by one thing. We are being moved by the combination of a pull toward density and a push away from emptiness, Both of those things are real. Both are measurable. Both have been confirmed. We are inside a hole, and we are being pushed out of it. The push and the pull are pointed in the same direction, and we have been moving at this velocity for billions of years. The local void itself needs to be described more carefully, because it is easy to imagine it wrong. When most people hear the word void, they imagine a hole, a spherical gap, a clean absence with sharp edges, a place where something used to be and has since been removed. The reality is messier and stranger than that. The local void is a region of space roughly 150 million light-years across, sitting adjacent to the local group and extending outward in one broad direction of the sky. It is not spherical. Voids rarely are. They tend to be elongated, sometimes irregular, shaped by the gravitational tug of the surrounding structure that pulled their matter out over billions of years. The local void is a somewhat oblong, irregular region, extending further in some directions than in others. 150 million light-years. Consider that for a moment. Our galaxy is 100,000 light-years across. The local void is 1,500 Milky Ways in diameter. It is a region in which you could fit 1,500 Milky Way galaxies laid end to end from one side to the other. And it is mostly empty. The local void is on the far side of the local group from Laniakea's attractor. If you imagine the Milky Way as a ship, the great attractor is roughly ahead of us, pulling. The local void is roughly behind us and to the side, pushing. The void extends primarily in the direction away from the Virgo cluster and the great attractor, roughly in the direction of constellations like Hercules and Bootes as seen from Earth. It is not completely empty. No void is. There are stray galaxies inside the local void, individual systems that happened to be in the wrong place when the surrounding matter drained away and were left behind. These galaxies are called void galaxies, and they have unusual properties that have been studied in detail. They tend to be more isolated than galaxies in filaments. They tend to be smaller, more gas-rich, with quieter star formation histories. They have fewer neighbours to interact with, fewer mergers to disrupt them, fewer collisions to trigger bursts of star formation. The environment inside a void shapes the galaxies that remain in it. If the Milky Way were a void galaxy deep inside the local void rather than near its edge, it would likely be a different kind of galaxy. Fewer mergers, fewer gravitational interactions, possibly a different structure. Being near the edge of the void rather than deep inside it means the Milky Way has had more gravitational interaction with neighbouring systems than a true void galaxy would have, including the eventual merger with Andromeda that is billions of years in the future. The local group itself, the small galaxy cluster that contains the Milky Way, Andromeda, the Triangulum Galaxy, and several dozen smaller companions, sits at what cosmologists sometimes describe as the edge of the void, at the boundary between the near emptiness of the local void and the greater density of the structures beyond it. Being at the edge of a void means being in a specific kind of cosmic location. You are in a position where the void's underdensity is real and measurable on one side, and the higher density of the surrounding structure is real and measurable on the other. You sit at a boundary, and that boundary has consequences that show up in the most careful measurements modern cosmology has made. This is where the story gets genuinely uncomfortable for modern cosmology. There is a number that sits at the heart of modern cosmology and has caused more debate among physicists in the past decade than almost any other measurement. It is called the Hubble constant. The Hubble constant measures the rate at which the universe is expanding. It describes how fast space itself is stretching, how quickly the distance between galaxies that are not gravitationally bound to each other grows with time. It is usually written as kilometers per second per megaparsec, which means how many extra kilometers of distance are added per second for every megaparsec of separation. A megaparsec is about 3.26 million light-years. The constant is named after Edwin Hubble, who in 1929 published the first clear evidence that distant galaxies are receding from us at speeds proportional to their distance. The greater the distance, the faster the recession. This was the first observational evidence that the universe is expanding. The constant that describes that rate of expansion took his name. The Hubble constant is central to almost everything in modern cosmology. The age of the universe depends on it. If the universe is expanding at a certain rate today, working backward tells you how long ago everything was concentrated in one place. The large-scale structure models depend on it. The dark energy calculations depend on it. The predictions for the universe's future, whether it will expand forever or eventually slow and reverse, depend on getting the expansion rate right. And cosmologists cannot agree on what it is, not because they have not measured it. They have measured it. Repeatedly with extraordinary care. With multiple independent methods, using different instruments, different calibration techniques, different types of objects as distance markers. The problem is that the measurements disagree with each other in a way that cannot easily be explained by measurement error. The two main camps of measurements give values that differ by about 8 to 10%. That sounds small. It is not small. In physics, when two careful measurements of the same quantity using independent methods disagree by 8 to 10%, with each measurement having its own internal uncertainty of only 1 to 2%, the gap between them is statistically significant. It cannot be explained by either team being slightly wrong. Something deeper is going on. One camp measures the Hubble constant from the early universe. The Planck satellite, operated by the European Space Agency, produced the most precise measurement of the CMB ever made. The Hubble constant derived from fitting the standard cosmological model to Planck's CMB data comes out to roughly 67 to 68 kilometers per second per megaparsec. The other camp measures the Hubble constant from the nearby universe using what is called the cosmic distance ladder. The ladder works by calibrating distances at multiple steps. First, the distances to nearby stars are measured using parallax, the apparent shift in a star's position as Earth orbits the Sun. Then those distances are used to calibrate the period-luminosity relationship of Cepheid variable stars, which pulse with a regularity linked to their intrinsic brightness. The Cepheids are then used to calibrate the brightness of Type Ia supernovae, stellar explosions that reach a known peak brightness. The supernovae are bright enough to be seen at great distances, far outside our local group, where they can be used to measure the recession velocity and therefore the expansion rate. The most refined version of this measurement, associated primarily with the work of Adam Ries and the S-NeuroES collaboration, consistently gives a value around 73 kilometers per second per megaparsec. 68 versus 73. Both measurements are precise. The uncertainties are small. The gap between them is real. Something is wrong somewhere, and physicists call it the Hubble tension. There are many proposed explanations for the Hubble tension, ranging from new physics in the early universe to modifications of dark energy to new types of particles. Most of those explanations require changes to the standard cosmological model that has worked so well for 3 decades. But one of the simpler proposed explanations is the one that connects directly back to where we are. We are inside a void. Here is the idea, and it requires care to explain without overclaiming. When cosmologists measure the Hubble constant from the nearby universe, from Cepheid stars and supernovae and galaxies within a few hundred million light-years, they are measuring the expansion rate inside the local void and its immediate surroundings. When cosmologists measure the Hubble constant from the early universe, from the CMB, they are measuring the expansion rate averaged across the full visible universe, 93 billion light-years of space in every direction. If the local universe, the region we are in, is a void, then the local expansion rate may be slightly different from the global average. Here is why. A void is a region where matter has drained away to the surrounding walls. The density inside a void is lower than the cosmic average, and the density of matter affects the expansion rate. In a denser region, gravity slows expansion slightly, because gravity opposes the expansion. In a less dense region, gravity does not slow it as much, so expansion runs slightly faster. This is a real physical effect predicted by general relativity and confirmed in simulations. The effect is sometimes called the void's outflow. Matter inside a void is not just sitting still, it is being moved outward toward the void walls by the gravitational pull of the denser surrounding regions. This outflow creates an expansion-like effect inside the void that adds to the background cosmic expansion. The local expansion rate inside a void, measuring how fast nearby objects appear to be moving apart from each other, will appear slightly higher than the global average, because it includes both the background expansion and the outflow. If we are inside a void, we may be inside a region where local expansion is running slightly faster than the global average. When astronomers at Earth measure the distance and recession velocity of a supernova in a galaxy a few 100 million light-years away, they measure a recession that includes both the background expansion and the local outflow contribution. That combined rate gives a Hubble constant that is slightly high relative to the true global rate. This could in principle explain why measurements from nearby supernovae and Cepheids give a higher Hubble constant than measurements from the CMB. The nearby measurements are sampling a locally fast expanding void region where the outflow boosts apparent recession. The CMB measurement is giving the global average unaffected by local structure because it averages over the full observable universe. The difference between the two is what you would expect if we are in an underdense region that has a local outflow. This idea is called the local void hypothesis for the Hubble tension, or sometimes the Hubble bubble explanation. It was proposed and explored by several research groups. Tom Shanks and collaborators at Durham University used supernova datasets to explore how a local void could affect Hubble constant measurements. Others have used galaxy survey data to estimate the magnitude of the void's effect. The idea is not proven. The community is divided on whether the local void is large enough and underdense enough to explain the full observed tension. Some analyses suggest the void's effect on local measurements accounts for only a fraction of the gap, perhaps 1 or 2 kilometers per second per megaparsec, rather than the full 5 or 6 needed. Others argue that with improved void characterization and careful treatment of the surrounding large-scale structure, the effect could be larger than initial estimates suggested. What is not in dispute is the logic. If you are making measurements of the universe's expansion rate from inside an underdense region, your measurements will have a local bias relative to the global average. The void introduces a systematic effect into the data. The question is quantitative: how large is that effect? And is it large enough to explain the observed tension? The most honest summary is this: the void is probably contributing something to the Hubble tension. It is very likely not the only explanation, and it may not be the primary one, but it may be part of the answer, and it is the part that is most directly connected to where we live. We are not neutral observers of the cosmos. We are observers inside a specific cosmic environment, and that environment shapes what our measurements see. The void is not just the context, it is a variable in the calculation. This is a subtle but important point for how we think about scientific objectivity. In physics, the ideal observer is imagined as standing outside the system being studied, making measurements without affecting the system and without being affected by it. That ideal observer does not exist. All observations are made from somewhere. All measurements are made from inside some environment. The question is not whether the observation is located, because it always is. The question is whether the location has been accounted for. For centuries, the location of the Milky Way in the cosmic web was not accounted for in cosmological measurements. Not because astronomers were careless, but because the tools to identify and characterize that location did not yet exist. The surveys that revealed the local void, the measurements that defined Laniakea, the flow analyses that quantified the void's contribution to our motion, are all products of the last few decades of observational astronomy. Before those tools existed, the location could not be accounted for because it was not known. Now it is known, and accounting for it is part of what the next generation of cosmological measurements needs to do. The CMB measurements come close to this ideal in some ways, because the CMB averages over the full observable universe and is less sensitive to local conditions. But the direct measurements of the universe's expansion rate, the Cepheid distances, and the supernova recession velocities are made from inside the system. They are made from inside the void. They cannot be made from outside it. This does not make the measurements wrong, it makes them located. They are measurements of the universe as seen from a specific place, and that place has specific properties that differ from the average. Accounting for the location is not a correction to the data. It is part of interpreting the data correctly. The same principle applies more broadly. Every telescope ever built, every spectrum ever taken, every photograph of the night sky ever made was made from inside this void. Our entire observational history of the universe was made from this specific cosmic location. The picture of the universe we have assembled over centuries of astronomy was assembled from inside the whole. The whole was always there, we just did not know it until recently. And knowing it changes how we read the picture. There is another way the void affects what we see, and it is more immediate than the Hubble tension. It affects the number of galaxies in the sky. This sounds like a trivial observation. More galaxies are visible in some directions than others because the universe is not uniform. That much is expected. But the local void produces a specific signature in the directions where the void lies. The galaxy count is measurably lower than average. Not slightly lower, significantly lower. Astronomers studying the distribution of galaxies in the local universe have long noticed an underdensity in certain directions, a region where, when you count galaxies up to a certain distance, you find fewer than the average predictions suggest. This underdensity is the observational signature of the local void. The effect was identified clearly in the 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey, which mapped the distribution of hundreds of thousands and then millions of galaxies across large portions of the sky. These surveys showed, with high statistical confidence, that the region around the Milky Way is underdense relative to the cosmic average. The galaxy count in the void directions is lower. The mean separation between galaxies in our local neighbourhood is larger than the cosmic average. We are in a thinner part of the web. Galaxy surveys that have tried to build complete catalogues of nearby galaxies have had to carefully account for this underdensity when calibrating their results. The fact that we are in an underdense region means that our local galaxy sample is not representative of the universe as a whole. If you drew conclusions about the average properties of galaxies in the universe by studying only the galaxies nearest to us, you would get a biased picture. The galaxies near us are, on average, somewhat more isolated and somewhat less clustered than the cosmic mean. This matters for a specific reason that connects back to how cosmology is done. Many of the foundational measurements in cosmology are made using nearby objects as calibrators. The distance ladder that underpins the local Hubble constant measurement relies on observing Cepheid stars and supernovae in nearby galaxies. Nearby means inside or near the local void. The galaxies used to host those Cepheid and supernova measurements are not in the cosmic average environment. They are in a void environment. And the void environment, with its slightly faster local expansion and its gravitational outflow, may have subtly shaped the statistics of those measurements. The void is not just a hole in the galaxy map, it is a systematic source of potential bias in the instruments we use to measure the universe. There is something unsettling about that. Cosmology has spent decades refining its instruments and its measurements to extraordinary precision. The Planck satellite measured the CMB to better than 1 part in 100,000. The supernova teams have cross-checked their calibrations in dozens of ways and with increasingly sophisticated methods. And yet, sitting here inside a void, the possibility exists that a fundamental fact about where we are has been quietly introducing a systematic bias into some of the most important measurements in modern physics. Not a catastrophic bias, not one that overturns everything, but a real physical measurable bias that comes from making observations from inside a specific kind of cosmic environment. We have been measuring the universe from inside a hole, and we are still working out exactly how much that matters. The environment inside a void does not just affect measurements and expansion rates, it affects the galaxies themselves. Astronomers have spent significant effort comparing the properties of galaxies inside voids, called void galaxies, to galaxies in denser environments like filaments, clusters and walls. The results show that environment, including the extreme environment of a cosmic void, leaves a measurable signature in galaxy properties. Void galaxies tend to be smaller. Without the gravitational interactions of a dense environment, smaller systems do not get pulled into mergers as often. Mergers build big galaxies. In a void, where neighbours are far apart and encounters are rare, the merger rate is low, and galaxies tend to grow more slowly and stay smaller. Void galaxies tend to be bluer. The colour of a galaxy reflects its star formation activity. Young, massive stars are blue, and they burn out quickly. Older stellar populations are redder. Galaxies in dense clusters often have their star formation quenched by interactions with the cluster environment, which can strip their gas and shut down the formation of new stars. Void galaxies, isolated from the cluster environment, tend to retain their gas supply and continue forming new stars, making them bluer. Void galaxies tend to have different morphologies. In clusters, galaxies that were once spiral tend to be transformed by interactions into elliptical galaxies. In voids, spirals are more common because the transformation mechanism is absent. All of these differences are real and measurable in galaxy surveys. They confirm that the void environment is not the same as the average environment. Living inside a void, even near its edge, means being in an environment that shapes the galaxies around us in specific ways. The Milky Way itself shows some of the properties that might be expected from a galaxy near the edge of a void. It is a large spiral, which is consistent with a relatively merger-free history, though the Milky Way has certainly had mergers in its past. The ongoing approach of the Andromeda Galaxy and the eventual merger is an exception in a generally quiet local history, not the rule. The Milky Way's star formation history has been relatively steady rather than dominated by starburst events, which are more common in merger-driven galaxy formation. This is consistent with an environment that has been quieter than the inside of a dense cluster, though the exact contribution of the void environment to the Milky Way's specific history is difficult to isolate from other factors. What this shows is that the void is not just a cosmological detail. It is the environment in which our galaxy formed and evolved. The specific properties of the Milky Way, whatever they are, were shaped in part by the gravitational and environmental context of the local void and the edge of the Laniakea supercluster. The galaxy you look at when you look at the Milky Way is a void-edge galaxy, with all that implies for its history and properties. There is an interesting question lurking here about the relationship between galactic environment and the development of something like life. It is speculative, but it is worth raising. Galaxies in dense clusters tend to have more frequent interactions, more gravitational disruptions, more bursts of intense star formation followed by quiescence. These are not obviously hospitable conditions for the development of complex chemistry and the slow evolution of living systems over billions of years. A galaxy that is regularly disrupted by mergers, whose stellar populations are periodically reshaped by starbursts, may not provide the stable chemical environment that allows planetary systems to build up the heavy element inventory needed for rocky planets and complex chemistry over long timescales. A galaxy at the edge of a void, in a quieter gravitational environment, with steadier star formation, with fewer cataclysmic mergers, might be somewhat more likely to provide the stable long-term conditions that allowed something like life to develop. This is speculative. The relationship between galactic environment and the emergence of life is not well understood, and the sample size of planets with known life is still one. But it is the kind of question that the void's existence raises. Is there something about being in an underdense region, about being in the quiet edge rather than the turbulent center, that made the Milky Way a more hospitable host for the particular process that eventually produced observers asking this question? Nobody knows. But the question is not unanswerable in principle. As the inventory of exoplanets grows, and as our understanding of galactic environments improves, the relationship between large-scale cosmic location and the possibility of complex chemistry may eventually be something that can be studied empirically rather than only speculated about. It is worth pausing here to be clear about something, because the word void carries implications that the actual object does not fully deserve. The local void does not feel like anything. You cannot sense it. The Earth is inside it the way a dust mote might be inside a large, mostly empty room. The room is enormous relative to the particle. The space inside is real, and the particle has no awareness of being inside a room rather than outside one. The void does not create a gravitational danger. It is not pulling matter toward a central collapse the way a black hole does. It is simply a region of lower density. The galaxies that have already drifted away from it are gone, moved on to the surrounding walls and filaments over billions of years. But nothing dramatic is happening inside the void itself. The matter that remains in the void is in stable motion. The local group, the Milky Way, the solar system, Earth, none of these are in any immediate physical jeopardy from the void. A useful comparison is to sea level and altitude. If you live at high altitude, the air is thinner. There is less pressure. There is less oxygen per cubic meter. This affects your physiology in measurable ways: breathlessness, lower boiling point of water, different ultraviolet exposure. But you are not in danger simply from the altitude itself. The difference in environment is real and has real consequences, but it is not a catastrophe. Living inside the local void is something like this, scaled up enormously. The environment is genuinely different from the cosmic average. That difference has real measurable consequences. But it is not a danger. What the void does is more subtle than danger. It shapes the gravitational environment. It creates the background against which everything in the local universe moves. The Milky Way's motion, at over 370 kilometers per second relative to the CMB, is partly a result of the void pushing from one side and Laniakea's mass pulling from the other. That motion has been happening for billions of years. The local group has been drifting through the void's edge, slowly moving toward the greater density of the structures beyond. In the very long run, billions of years from now, if the current motion continues and is not significantly altered by future gravitational interactions, the local group will be further from the void center than it is today. We are already near the edge of the void, and the edge is, on cosmological timescales, a region in transition. The void will continue to expand, as voids do. The matter at the void's edges, which is being pulled toward the surrounding filaments and walls, will continue to drain away, making the void emptier over time. Voids grow. They do not shrink. In an expanding universe with dark energy driving accelerating expansion, structures that are already underdense become progressively more underdense. The matter that could have fallen back in is instead being accelerated outward as dark energy dominates on ever larger scales. The cosmic web's filaments will become thinner, the clusters more isolated, the voids more dominant. The universe's future, if current models are correct, is one in which voids get larger and the walls that separate them become more tenuous and more isolated. The cosmic web will become more skeletal over time, not less. The voids will dominate more and more of the universe's volume. We are inside the future majority of the universe. That is not a danger, but it is a different way to understand what kind of place this is. The most difficult part of mapping the local cosmic structure is that a large portion of it is hidden from us. Not hidden in an exotic way, hidden by our own galaxy. The Milky Way is a disk of stars, gas, and dust roughly 100,000 light-years across. From Earth's position inside this disk, we look out through the plane of the galaxy in every direction that lies along the galactic equator. In those directions, the view is blocked by the galaxy's own material. The dust in the Milky Way's disk absorbs and scatters the light from background objects. Stars that lie behind dense dust clouds are invisible in optical telescopes. Distant galaxies behind the galactic plane are similarly obscured. The region of sky that falls within roughly 10 to 20 degrees on either side of the galactic plane is called the zone of avoidance, because early galaxy surveys simply avoided cataloguing those regions. The name reflects the practical reality. Early sky surveys could not map what they could not see, and what they could not see was a wide band of sky that happened to contain a significant fraction of the surrounding universe. The zone of avoidance presented a real problem for mapping the local cosmic structure. The great attractor, the mass concentration that draws our part of the universe toward it, lies in the direction of the constellation Centaurus, at a galactic latitude that places much of the associated mass structure within or near the zone of avoidance. A significant portion of the mass concentration driving our local cosmic flow was, for decades, behind the plane of our own galaxy. This created an ironic situation. The largest mass structure in our immediate cosmic neighborhood, the one most responsible for the motion of hundreds of thousands of galaxies including our own, was partially hidden by our own galaxy's disk. We were being pulled towards something we could not see clearly. The map of local cosmic flows had a gap in the most important region. This is not a unique situation in astronomy. Some of the most important nearby structures in the universe have been among the hardest to study, simply because they lie in awkward directions from Earth. The galactic center itself, the center of the Milky Way, is obscured by so much dust that it was not even identified as the center of the galaxy until radio observations in the mid-20th century revealed it. The center of our own galaxy, the most massive object in our immediate neighborhood, was invisible to optical astronomy for most of human history. The zone of avoidance and the Great Attractor are a scaled-up version of the same problem. Important things in important directions, hidden by intervening dust. Astronomers developed several strategies to see through this obscuring band. Radio waves pass through dust more easily than optical light, so radio surveys of galaxies could probe regions that optical surveys could not. Infrared observations, similarly, suffer less from dust absorption than visible light observations, so infrared galaxy surveys have been important tools for mapping the zone of avoidance. One of the key results from these efforts was the identification of the Norma cluster, a massive galaxy cluster in the Norma constellation that was hidden behind the galactic plane and only revealed through radio and infrared observations. The Norma cluster turned out to be one of the most massive clusters in the nearby universe, a major contributor to the gravitational pull of the Great Attractor region. Without the ability to see through the zone of avoidance, a significant piece of the local gravitational landscape would have been missing from the maps. More recently, the Parkes Radio Telescope in Australia was used to conduct the HIPAS survey, a systematic search for hydrogen emission from galaxies across the entire southern sky, including through the zone of avoidance. Hydrogen gas in galaxies emits radio waves at a characteristic wavelength of 21 centimeters, a signal that passes through the Milky Way's dust with minimal obstruction. The survey found numerous previously uncatalogued galaxies hiding in the zone. In 2016, a study led by René Kraan-Korteweg and collaborators used the Parkes telescope to systematically map the Vela supercluster, a massive concentration of galaxies that had been almost entirely hidden in the zone of avoidance. The Vela supercluster, at a distance of roughly 800 million light-years, turned out to be one of the largest superclusters in the nearby universe, comparable in mass to the Shapley concentration, and it had been entirely invisible, hiding in the galaxy's shadow, until radio observations revealed it. The lesson from the zone of avoidance is that mapping the local universe is an ongoing process, not a completed one. Significant structures have been missed simply because they were in the wrong place relative to the plane of our own galaxy. As observational techniques improve, as infrared surveys become more powerful and radio surveys more sensitive, the map of the local cosmic web is still being filled in. The void we live in and the supercluster we are part of were mapped against the background of incomplete information about what surrounds us. The picture has improved dramatically over the past few decades, but pieces are still being added. The next generation of surveys, including the Vera Rubin Observatory's Legacy Survey of Space and Time, the Euclid Space Telescope launched by the European Space Agency in 2023, and the Nancy Grace Roman Space Telescope planned for later in the decade, will map the large-scale structure of the universe to greater depths and with greater precision than any previous survey. Euclid in particular is designed to map the cosmic web across billions of light-years and measure the properties of dark energy with unprecedented precision. The void statistics from those surveys, how many voids of each size exist, and how their properties compare to theoretical predictions, will be used to constrain dark energy models. The local void will continue to be refined as more data on nearby galaxy distances and peculiar velocities accumulates. The Cosmic Flows project will continue adding galaxies to its catalogue. The forthcoming surveys will overlap with the local volume and add galaxies that the current surveys missed. The shape, depth and extent of the local void, already much better characterized than it was 20 years ago, will be mapped with increasing precision. We are inside a hole that is still being measured. We are not in the dense center of the universe. We are near the edge of a void, in a region that is, on very long timescales, losing material to the surrounding walls and becoming emptier. This is not a comfortable framing, but it is an accurate one. The discovery of Laniakea and the local void changed something in the way cosmologists think about the local universe. Before that 2014 paper by Tully and collaborators, the concept of a supercluster was defined purely by the proximity and density of galaxies. Superclusters were recognized as large galaxy concentrations, but their boundaries were fuzzy, and different astronomers drew them differently. Our local supercluster was previously identified as the Virgo supercluster, a smaller structure centered on the Virgo cluster. The gravitational flow approach changed that, by mapping which galaxies are actually flowing toward the same attractor. The Laniakea study showed that the Virgo supercluster is just one part of a much larger gravitationally coherent structure. Laniakea is not a loose collection of galaxies that happen to be near each other. It is a structure that is dynamically connected, a gravitational watershed in which every galaxy is sliding toward the same basin of attraction. The idea of a gravitational watershed is the right analogy here. Imagine a mountain range. On one side of the mountain, all the water flows toward one ocean. On the other side, all the water flows toward a different ocean. The watershed is the line that separates the two drainage basins. A drop of rain that falls precisely on the ridgeline could go either way. A drop that falls on one side is committed to one drainage path. There is no mixing. The watershed divides the landscape into regions of distinct gravitational fate. In the cosmos, superclusters are gravitational drainage basins. Inside Laniakea, every galaxy is moving toward the same attractor, the Great Attractor region. On the other side of Laniakea's boundary, galaxies flow toward different attractors, toward the Perseus-Pisces supercluster to one side and the Coma supercluster to another, or further still toward the massive Shapley concentration. The boundary of Laniakea is the line at which the gravitational flow changes direction. Cross that boundary and you are in a different watershed, a different supercluster, a galaxy that will spend the next billions of years flowing toward a different center of mass. The Milky Way sits well inside the Laniakea watershed. Its fate, gravitationally speaking, is tied to the attractor at Laniakea's center. This is new geography, not geography of surfaces and elevations, geography of gravitational flow in 3 dimensions, spread across hundreds of millions of light years, invisible to telescopes that only see light, but revealed by the systematic mapping of galaxy motions. The watershed model also shows something else. The boundary between Laniakea and the neighbouring Perseus-Pisces supercluster passes through a region of relatively low density, a filamentary structure connecting the two systems. On the Laniakea side, matter flows one way. On the Perseus-Pisces side, matter flows the other. The boundary is not a physical wall, it is a line of zero net gravitational pull, where the attraction from one side exactly balances the attraction from the other, and it revealed that the structure surrounding the local void is not just a dense region adjacent to where we are, it is the basin into which we are flowing. The void is expelling us into the watershed. We are inside Laniakea not just by position, but by dynamics. We are drifting, very slowly, toward the center of the largest gravitationally coherent structure that has ever been mapped. The void and the supercluster are not separate stories. They are two sides of the same story. The motion of the Milky Way through the cosmic web, pushed by emptiness and pulled by mass, embedded in a structure that human observers have only recently developed the instruments to recognize and map. There is something particular about the era in which we live that makes the local void scientifically visible in a way it would not have been in the past, and may not be in the far future. The cosmic microwave background will not always be detectable. As the universe continues to expand, the wavelength of the CMB is stretched further and further. It becomes colder, longer wavelength, harder to detect. 1 trillion years from now, the CMB will have been redshifted to wavelengths so long and temperatures so close to absolute zero that the background noise of other radiation sources will completely overwhelm it. A civilization existing in the universe at that time would have no way to detect the CMB the way we do. They would not know about it from observation. They could only know about it by inheriting our records. More than that, the accelerating expansion of the universe is pushing distant galaxies away faster and faster. The boundary of the observable universe, the distance beyond which light can no longer reach us because space is expanding too fast, is not a fixed feature. In an accelerating universe, that boundary gradually contracts in terms of the number of galaxies we can observe. Galaxies that are currently visible to us are receding. Some are already receding faster than the speed of light due to the expansion of space. In the very long run, they will redshift to invisibility, their light stretched into wavelengths too long to detect. The observable universe for any civilization trillions of years from now will be far smaller and far emptier looking than the one we observe today. A physicist in the far future, living in the Milky Way after the merger with Andromeda and the long dispersal of the cosmic web, might look out at a universe that appears to consist of a few hundred gravitationally bound galaxies in the local cluster, Milky and its companions surrounded by absolute darkness. The distant universe, the filaments and superclusters and CMB and large-scale structure would be unobservable. Our records, if preserved, would seem to describe a universe far richer and more complex than what their instruments could show. They might struggle to believe us. We live at a moment in cosmic history where the evidence for the large-scale structure of the universe, the voids, the filaments, the superclusters, the CMB, the cosmic flows, is all still accessible. The data is still arriving. The signals are still strong enough to measure. Future civilizations, even 1 billion years from now, may live in a universe that looks more uniform from their instruments, simply because the evidence that it is not uniform will have expanded beyond their observational reach. This is a strange thought, that we may be living at a privileged moment in cosmic time. Not privileged in any special sense, not because humans are significant, but because the instruments of cosmological knowledge, the CMB, the redshifts of distant galaxies, the large-scale structure visible to our telescopes, are available to observers now in a way they will not always be. The window is open, we are looking through it. And one of the things that measurement has revealed at this particular moment in cosmic history is that we are inside a void. We are inside a structure that has been draining for billions of years. We have been measuring the universe from an underdense location. The window is showing us our own address. That fact is now available to us, and it has implications for everything from the Hubble tension to the way we calibrate our deepest distance measurements. We are reading our own location in the cosmic web at the moment in history when reading it is still possible. The privilege of this moment extends beyond the CMB. The large-scale structure surveys that map the positions of millions of galaxies to trace the cosmic web require that the galaxies being mapped are close enough and bright enough to detect. As dark energy drives the expansion to accelerate, galaxies at the current edge of our surveys will, over billions of years, recede beyond the cosmological horizon. The observable universe we can survey is contracting in terms of the fraction of the total universe we can access. Right now we can see billions of light years in every direction. We can map the cosmic web to large distances, we can measure peculiar velocities of nearby galaxies and use them to trace the gravitational flows that reveal the void and the supercluster. All of this is accessible because the universe is at the right age. We are inside a brief window, cosmologically speaking, where all these signals are strong enough to detect and interpret. In some sense, the void we are inside made itself easier to find by sitting near the edge of the void, in a region of lower density with a supercluster on the other side. The local group has a measurable peculiar velocity. If we were in a perfectly average environment, the CMB dipole would be much smaller, the local cosmic flow much harder to detect, and the void much harder to map. The void announced itself through the motion it caused, and the motion is what told us the hole was there. We are inside the hole. The hole pushed us. We measured the push, and from the push we found the hole. The motion question deserves a cleaner summary, because it has several layers that can blur together. The Earth orbits the Sun at about 30 kilometers per second. That is the motion most people know, if they know any of these numbers. 30 kilometers per second means Earth covers about 940 million kilometers every year as it circles the Sun. The Sun orbits the center of the Milky Way at about 220 kilometers per second. One orbit of the galaxy takes the solar system roughly 225 to 250 million years. The last time the solar system was at this location in its galactic orbit, dinosaurs had not yet appeared on Earth. The one before that, multicellular life was still new. The galactic orbit is measured in intervals of deep biological time. The Milky Way and Andromeda are approaching each other at about 110 kilometers per second. They are currently about 2.5 million light-years apart. The approach is slow by galactic standards, and their actual merger will not happen for roughly 4 to 5 billion years. When it does happen, it will not be a collision in the ordinary sense. The space between stars is so vast that most stars will simply drift through the merge without hitting anything, though close gravitational encounters will scatter some stars into new orbits. The galaxies will distort each other's shapes, exchange stars, and eventually settle into a single merged galaxy, which astronomers have informally named Milky Way. The eventual merger with Andromeda is not a consequence of the void or the supercluster directly. It is a consequence of the fact that the Milky Way and Andromeda are gravitationally bound to each other in the local group, close enough and massive enough that their mutual gravity overcomes the expansion of space between them. On very large scales, dark energy's expansion wins and galaxies separate. On the scale of the local group, gravity wins and the galaxies approach. After the merger with Andromeda, the resulting galaxy will still be part of the local group, still part of Laniakea, still being pulled toward the great attractor, still near the edge of the local void. The void will be larger by then, emptier by then, with the matter that once occupied it having drained further toward the surrounding walls. But the local group, gravitationally bound together, will remain a coherent structure even as the rest of the universe expands beyond reach. What eventually happens to the local group, billions and billions of years after the Milky Way-Andromeda merger, depends on timescales and physical processes that are genuinely uncertain at that range. But the local group will continue to exist as a gravitationally bound island long after the cosmic web's filaments have thinned beyond recognition and the distant universe has receded beyond observation. The local group, our cluster of galaxies, is moving toward the Virgo cluster at about 200 to 250 kilometers per second, pulled by Virgo's enormous mass concentration 65 million light-years away. And the entire local universe, the local group, the Virgo cluster, the thousands of galaxies participating in the Laniakea flow, is moving toward the great attractor region at several hundred kilometers per second. When all of these motions are combined and compared to the reference frame of the cosmic microwave background, the total peculiar velocity of the Milky Way, the velocity relative to the ancient radiation that fills all of space, comes to roughly 370 kilometers per second. more than 1,000,000 kilometers per hour. In a specific direction in the sky, toward the constellation Leo, slightly toward the Great Attractor and away from the local void. None of these motions cancel each other. They add in specific directions. The result is not random jitter. It is a coherent drift, the Milky Way and everything inside it travelling in a particular direction at a particular speed, driven by the gravitational landscape of the local universe. This is the total motion. It is not a single cause. It is the accumulated result of every gravitational environment we are embedded in, from the solar system scale to the supercluster scale, all of them adding their contribution to a vector that points us through the ancient radiation field at extraordinary speed. And the key piece that the void adds to this picture is the push from behind. The local void is not pulling us toward itself. It is, in the language of dynamics, contributing a repulsive term, not through any mysterious force, but simply because it has less gravity than the surroundings, and we are therefore drifting away from it toward the denser regions. The void's contribution to our velocity is in the same direction as Laniakea's pull. They cooperate. They sum. We are being pushed and pulled in the same direction, and we have been for billions of years, and we are only now, in the last few decades of astronomical history, beginning to have the instruments sensitive enough to map all of this in enough detail to say it clearly. What does it mean to be inside a void? Not physically, not in terms of any danger or disruption, but conceptually, in terms of what it says about the mental model of the universe that most people carry. Most people, when they think about where they are in the universe, think in layers. The Earth is inside the solar system. The solar system is inside the Milky Way. The Milky Way is inside the local group. The local group is inside the universe. The universe is large and mostly uniform. That last assumption, mostly uniform, is the one that the large-scale structure of the cosmos quietly corrects. The universe is not mostly uniform at the scale of hundreds of millions of light years. It is structured. It is organized into voids and walls and filaments and nodes in a way that has specific, measurable consequences for where things are, how fast they move, and what the universe looks like from inside different parts of that structure. The structure is not a background detail. It is the main fact about the universe at large scales. Think about what changes when you know this. If you were a cosmologist working on the CMB and the Hubble constant, knowing you are inside a void changes your interpretation of your supernova measurements. You have to consider whether the local expansion rate you are measuring with nearby supernovae is the same as the global rate. You have to ask whether the void is introducing a systematic bias into your calibrations. If you were an astronomer studying galaxy properties, knowing you are near the edge of a void means knowing that the local galaxy sample may not be fully representative. The galaxies nearby are slightly spread out, slightly less clustered, slightly different in their environment than the average galaxy in the universe. Conclusions drawn from local galaxy samples have to account for that. If you are a cosmologist building models of the large-scale structure, knowing the geometry of the local void and the position of the local group relative to it changes the predictions for the local gravitational flow, the peculiar velocities, the expected distribution of matter around us. In each of these cases, the location is not a curiosity. It is a variable that enters the calculation. We are inside a specific part of the cosmic structure. We are near the edge of a void. We are inside a supercluster. We are flowing toward a gravitational attractor. We are being pushed away from a region of underdensity. All of this is happening continuously and has been happening for billions of years. The mental model of the universe that most people carry treats the Milky Way as being inside a roughly average piece of the cosmos, an ordinary location, a place without particular significance in the large-scale structure. That model is not accurate, not dangerously inaccurate, not wrong in a way that matters for everyday life, but inaccurate in the specific, technical, measurable sense that our location has a character, and that character shows up in the data. We are in a void. We are near the edge of that void. We are inside the Laniakea supercluster. We are one of the galaxies being swept toward the Great Attractor. We are, in the gravitational sense, part of a massive slow drainage event that is consolidating hundreds of thousands of galaxies into an enormous basin of gravitational attraction over billions of years. This does not make us special in any cosmic sense. Being inside a void is not unique. Many galaxies are. But knowing that we are inside a void is important because it changes what we expect our measurements to show, what biases our instruments might carry, and what the universe looks like from here versus from somewhere else. The location is specific. The specificity has consequences. And the consequences are still being worked out. The Hubble tension, which began this part of the story, has not been resolved. As of recent years, the gap between the early universe measurement of the Hubble constant and the late universe measurement has remained stubborn. The precision of both measurements has improved. The teams on both sides have cross-checked their calibrations repeatedly, looking for systematic errors, testing new calibration techniques, using new types of objects. Gravitational wave measurements from merging neutron stars have been used as an independent calibration of the Hubble constant. When two neutron stars spiral into each other and merge in an event called a kilonova, they produce both a gravitational wave signal and a flash of light. The gravitational wave signal carries information about the distance to the merger, because the shape and loudness of the signal depend on the masses and separation of the orbiting bodies in a way that can be calculated precisely. The light signal provides the redshift. Combining the two gives a Hubble constant measurement that is completely independent of the Cepheid ladder and the CMB. The kilonova measurements give a Hubble constant somewhere between the two competing values, with uncertainties still large enough that they are consistent with both camps. More kilonova events, detected by gravitational wave observatories, will eventually sharpen this measurement. Measurements from masers, water molecules in distant galaxies that emit microwave radiation like natural microwave lasers, have been used to measure distances with a completely different technique. Maser measurements give distances to specific galaxies with high precision, bypassing the Cepheid step in the distance ladder. These measurements have tended to support the higher Hubble constant value. The James Webb Space Telescope has been used to check the Cepheid calibrations that underpin the supernova distance ladder. One long-standing concern about the local Hubble constant measurement was that Cepheid observations by the Hubble Space Telescope might have been affected by crowding, the blending of light from multiple stars in dense stellar fields. Webb's sharper infrared images have allowed astronomers to check this. Early Webb results, published in 2023, found that the Cepheid measurements appear to be robust and not significantly affected by crowding, strengthening confidence in the local Hubble constant value of around 73. The tension has not gone away. If anything, the improved precision has made it look more like a real signal and less like a calibration error. The statistical significance of the tension has been estimated at several sigma, meaning that if the two measurements were measuring the same thing with no systematic difference, the probability of seeing a gap this large by chance is very small. Several types of new physics are being explored as explanations. Early dark energy, a form of dark energy that was significant in the early universe but faded before recombination, could alter the sound horizon scale used to calibrate the CMB Hubble constant. Interacting dark matter in which dark matter particles decay or interact in new ways, could also shift the early universe predictions. New light relativistic particles could change the radiation density in the early universe and shift the calibration. And some explanations involve the local structure. The void. The local structure explanations have a particular appeal because they do not require new physics. They explain the discrepancy as a statistical or environmental effect rather than a fundamental model failure. If we are in a void, and the local expansion rate is genuinely slightly faster than the global average because of the underdensity and the local outflow, then the supernova measurements are giving a real answer about the local expansion rate. And the CMB measurement is giving a real answer about the global average, and both are correct within their respective domains. The tension then is not a failure of the model, it is a failure to account for where the measurements are being made from. The honest answer is that the community does not know yet which explanation is correct, or whether the correct answer combines several contributing factors. It may be new physics, it may be local structure, it may be both, it may be something not yet proposed. What is clear is that the Hubble tension is real, that it is one of the most important open questions in modern physics, and that one of the proposed explanations for it is directly connected to where the Milky Way happens to be in the cosmic web. The question of where we are is not a philosophical question, it is a physics question, and the answer to it may be part of what unlocks the most stubborn measurement problem in cosmology. There is a way to experience the local void observationally, without any instruments, on a clear night in the right location. Look toward the constellation Bootes. Look further toward Hercules. Look in the direction of the sky that lies more or less opposite to the Virgo cluster, roughly the opposite direction from the Great Attractor and from the densest part of the surrounding structure. You are looking into the local void. Not at its centre. The void's centre is further away, hundreds of millions of light years in that direction. But you are looking into it, looking into a region where the galaxy count drops off, where the large-scale structure is thinner, where the cosmic web has fewer threads per unit volume. The sky in that direction contains the same familiar stars of the Milky Way as in any other direction. Those stars are local, inside our own galaxy, and the void is far beyond them. But if you could strip those stars away and look at the background of distant galaxies, the galaxy count would be lower, the web would be thinner, the void would be visible in its absence. This is how voids are detected, not as bright things, but as systematic gaps in the distribution of bright things. When galaxy surveys count the number of galaxies per cubic megaparsec in different directions and at different distances, the void shows up as a region where that count falls below the expected average. The absence is measurable. The gap has a shape and a size and a location. The void is mapped by the galaxies it does not contain. The Bootes void, discovered in 1981 by Robert Kirshner and colleagues, was one of the first large-scale voids to be identified in galaxy surveys. It is a roughly spherical void about 330 million light-years in diameter, in the direction of the constellation Bootes, and it is a much larger and deeper void than the local void. When the survey team found it, they described the experience of looking at the data, a huge region of sky containing almost no galaxies at all. The expected number of galaxies in that volume was 100. The actual number found was few. The Bootes void became one of the first clear demonstrations that voids are real, large-scale features of the universe, not statistical noise. The great irony of living inside a void is that the void is, in a specific sense, the thing we can see least clearly from inside it. The most distant galaxies in the far wall of the local void, the edge where it meets the first filaments and groups on the other side, are roughly 150 million light-years away. The light from those galaxies that is reaching us now left them 150 million years ago, before the asteroid impact that ended the non-avian dinosaurs, before the continents were quite in their current positions. We are seeing the void's boundary as it was 150 million years ago. The boundary exists right now, 150 million light-years away, in its current configuration. But we are seeing it as it was in deep geological time, in an era before our species existed or could be imagined. The void is real, current, surrounding us. But the information we have about it, the light that tells us it is there, is old. It has been travelling toward us since long before our species existed, since long before any primate existed, since before the mass extinction at the end of the Cretaceous, which happened roughly 66 million years ago, and even that was 84 million years after the void's wall light began its crossing toward us. Everything we know about where we are comes from ancient light reading us our current address. The address is real. The messenger carrying it is very, very old. The void exists inside a universe driven by dark energy, and dark energy has a specific relationship with structures like voids that is worth understanding. Dark energy is the name given to whatever is causing the universe's expansion to accelerate. The expansion of the universe, discovered in 1929 by Hubble and confirmed repeatedly since, was originally expected to be slowing down over time, because gravity should be pulling the matter of the universe together and resisting the expansion. In 1998, two independent research teams studying distant Type 1a supernovae made a discovery that won their leaders, Saul Perlmutter, Brian Schmidt, and Adam Ries, the Nobel Prize in Physics in 2011. The expansion is not slowing, it is speeding up. Something is driving the universe to expand faster and faster over time. That something is dark energy. The nature of dark energy is one of the deepest unsolved problems in physics. It might be the cosmological constant, a property of space itself that Einstein first proposed and then famously doubted. It might be a dynamic field that changes over time, what theorists call quintessence. It might be something more exotic. It might be a sign that general relativity needs modification at cosmological scales. Nobody knows. What is known is what dark energy does. On large scales, dark energy acts as a kind of repulsive pressure, accelerating the expansion of space and pushing distant objects further apart. In regions where matter is dense enough, gravity dominates over dark energy, and structures can still grow and cluster. In regions where matter is sparse, dark energy dominates. Cosmic voids are the environments where dark energy dominates most completely. Inside a void, the matter density is below the cosmic average. The gravitational pull from the sparse matter inside the void is weak. There is not enough gravitational force to resist dark energy's push. As a result, voids expand faster than the universe as a whole. The expansion inside a void is slightly faster than the background cosmic expansion rate. The matter at the void's edges is pulled outward by the surrounding structure's gravity and pushed outward by the dark energy inside the void, and the void grows. This makes voids a particularly interesting laboratory for studying dark energy. The size distribution of voids, how many voids of each size exist in the universe, and how that distribution changes over time, depends on the balance between gravity, which tends to pull matter toward density concentrations and away from voids, and dark energy, which drives the expansion that makes voids grow. By measuring the void size distribution precisely and comparing it to theoretical predictions, cosmologists can constrain the properties of dark energy. Survey telescopes like the Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and the upcoming Vera Rubin Observatory have all included void statistics as one of their science targets, precisely because voids are sensitive probes of dark energy. The local void we inhabit is therefore not just a feature of where we happen to be, it is a piece of dark energy's ongoing reordering of the universe. Dark energy is, very slowly, making voids bigger and filaments thinner. It is separating the universe into increasingly isolated islands of bound matter surrounded by increasingly empty voids. The cosmic web of today is a web. The cosmic web of 1 trillion years from now, if dark energy continues to accelerate expansion, will be something more like isolated dots in an expanding sea. We are inside one of the structures that dark energy is actively growing. The void is not a leftover from early structure formation that dark energy has forgotten. It is part of dark energy's ongoing work. This also means that the local void today is not the local void of the early universe. When the universe was young and dense, the density contrast between the void and its surroundings was much smaller. The region that would become the local void was underdense, yes, but not as dramatically underdense as it is now. Over billions of years, gravity amplified the density contrast. Matter drained away from the underdense region toward the denser surroundings. The void deepened. The walls grew denser. The contrast between the void interior and the void walls became more pronounced. This process is ongoing. The local void today is deeper than it was 1 billion years ago. The local void 1 billion years from now will be deeper still. Dark energy ensures that the process has no reversal. There is no mechanism that will replenish the void with matter, no force that will draw the drained material back in. Once matter leaves the void, pulled by the surrounding gravity, it is gone from the void's interior. The void is a one-way drain. The universe's future in this picture is one of progressive emptying of the voids and progressive isolation of the clusters. The filaments, which are already thin compared to the density of the clusters they connect, will thin further as dark energy drives expansion and the gravitational bond between distant structures weakens. Eventually, on timescales much longer than the current age of the universe, structures that are not gravitationally bound will no longer be able to influence each other at all, separated by the ever-accelerating expansion of space. In that distant future, the local void will be much, much emptier than it is today. The void that we are inside right now is a young void, cosmologically speaking. It is emptier than in the early universe, but not as empty as it will eventually become. We are catching the void in its middle age. This brings the question back to something simpler. What do you do with the knowledge that you are inside a void? Not in the practical sense. The void does not change daily life. The Hubble tension will not be resolved in any single person's lifetime through a single measurement. The motion toward the great attractor will not be perceptible in any human experience. The void does not affect the weather or the tides or the length of a day. But in the conceptual sense, the knowledge changes something. It changes the mental model of the universe from a place where we are in roughly the average situation to a place where we are in a specific situation. A situation with a specific gravitational history inside a specific large-scale structure with a specific environment that differs from the cosmic average in ways that are real and measurable. The average of the cosmic web is a filament, a place where matter has concentrated into sheets and strings, where galaxies are denser and neighbour interactions are more frequent. The average galaxy is in a filament, or at a node where filaments intersect, or in a cluster. The average galaxy has more neighbours than the Milky Way has. We are below average. We are in the underdense part. We are in the majority of the volume but the minority of the matter. there is something worth sitting with in this. Human intuition tends to place things at the center, or at least in the average. It is a natural cognitive bias, and it has been corrected before in the history of science. The Earth was thought to be at the center of the solar system. The solar system was thought to be near the center of the galaxy. The galaxy was thought to be in roughly the average environment of the universe. None of these turned out to be accurate. And now the picture has been refined further. Not only are we not at the center of anything, we are specifically in a below average density region, an underdense environment. The kind of place where the matter that used to be here has largely left, drained toward the surrounding walls over billions of years. This does not make us wrong or insignificant, it makes us located. And understanding the location is part of understanding what the measurements made from this location mean. It changes the way the measurements we make of the universe should be interpreted. When astronomers look at the expansion rate of the universe and find a number, that number is coloured by where they are making the measurement. The colour is real and has to be accounted for. The Hubble tension may partly be a consequence of measuring the universe's expansion from inside an expansion-boosting void. The galaxy statistics of the local universe may be slightly different from the cosmic average, because we are in a below-average environment. It changes the sense of what the dark is. Most people understand intellectually that space is mostly empty. But the empty of interplanetary space, the empty between stars, the empty between galaxies in a cluster, is empty in a way that still has structure nearby. The empty between galaxy clusters in a filament is a local gap in a web that is denser than average overall. The empty of a void is a different kind of empty. It is a structured absence. It is a region where the universe has, over billions of years, systematically removed its own matter, pulled it toward the walls, drained the local density down to something lower than the large-scale average. The matter that left is not coming back. The void will only get emptier as dark energy continues to drive expansion and pull the walls further away. We are inside that kind of empty. The vast majority of the universe, by volume, is this kind of empty, and we are part of that majority. The hole around us is not a black hole, not a catastrophe, not a warning. It is a description of where we are in the structure of the cosmos. It is a coordinate. And like all coordinates, it tells you something about the perspective from which every other measurement is made. Every time we look at the universe, we look at it from inside this hole. We have never looked at it from anywhere else. All of our observations, all of our calibrations, all of our maps of the cosmos, everything we have learnt about the size and age and expansion rate and future of the universe was learned from this specific location, inside an underdense region, near the edge of a supercluster, being pushed toward a wall and pulled toward an attractor, travelling at over 1 million kilometers per hour through the ancient light of the early universe. That is where you are. It always has been. And now, at this particular moment in cosmic history, when the instruments are sensitive enough and the surveys complete enough and the analysis sophisticated enough to say it clearly, we finally know it. The story of how the local void was found is not a single discovery, but an accumulation of findings across decades. In the 1970s and 1980s, as the first large-scale galaxy redshift surveys began to return data, astronomers noticed something in the galaxy distribution. In the direction of certain constellations, particularly in the region of sky away from the Virgo cluster, the galaxy count dropped. When they plotted the positions of galaxies in 3 dimensions, using redshift to estimate distance, they found regions of emptiness that were larger than expected from a random distribution of galaxies. The concept of a systematic structure in the universe's galaxy distribution, rather than random scatter, was still unfamiliar, and sometimes controversial. The idea that galaxies were arranged in filaments and surrounded by large empty regions was not immediately obvious from the data, and it required new analysis techniques to see clearly. Brent Tully and Richard Fisher, working in the 1970s and publishing a major catalogue of nearby galaxies in 1987, were among the early cartographers of the local universe. Their work on mapping galaxy distances using the Tully-Fisher relation, a way of estimating a galaxy's intrinsic brightness from its rotation speed, provided the distance data needed to build three-dimensional maps of the local galaxy distribution. As those maps improved, the local void became increasingly clear, not as a single announced discovery with a single date, but as a feature that revealed itself as more data was gathered and the maps became more complete. By the 1990s, the existence of a significant underdensity in the local volume of space adjacent to the local group was established and recognized in the literature. The name local void reflects both its proximity and its scale. It is local in the sense that it is the void immediately adjacent to our own galaxy cluster, the nearest large void to the Milky Way, and it is a void in the technical sense, a region of space with a galaxy density significantly below the cosmic average. The full extent and depth of the local void continued to be refined as surveys improved. The 2DF Galaxy Redshift survey in the early 2000s and the Sloan Digital Sky survey, which began returning data in 2000 and eventually mapped hundreds of millions of galaxies, provided the statistical power to characterize voids with much greater precision. The local void's dimensions, its shape, its relation to the surrounding filaments and walls were all sharpened by these surveys. More recently, the analysis by Hoffman and collaborators in 2017, using the Cosmic Flows 3 dataset of galaxy peculiar velocities, provided the most detailed reconstruction yet of the local gravitational environment, including the contribution of the local void to the peculiar velocity of the local group. They're finding that the void's repulsion contributes roughly as much to our total velocity as the attraction from Laniakea was a specific quantitative result that had been qualitatively expected but not previously measured with that precision. The discovery of where we are did not come in a single moment. It came in the way most of science comes, in pieces, from many researchers over many years, with each new instrument and each new dataset adding another layer of detail to a picture that was always there waiting to be assembled. There is something worth noting about the scale of human effort that went into finding this answer. The Cosmic Flows surveys, which produced the velocity data used to define Laniakea and characterize the local void's contribution to our motion, required measuring the distances and recession velocities of thousands of individual galaxies. Each measurement required telescope time, careful data reduction, calibration checks, and comparison with other measurements. The maps that resulted, the visualizations that show our galaxy as one small dot in a web of flows pointing toward the great attractor, represent years of cumulative observational work by large collaborations of astronomers. The Cosmic Flows project, led by Brent Tully and collaborators, has produced several data releases over the years, each one incorporating more galaxies and better distance measurements than the last. Cosmic Flows 1 provided a catalogue of around 1,800 galaxies with measured distances. Cosmic Flows 2 expanded that to nearly 8,000. Cosmic Flows 3, released in 2016, included over 17,000 galaxies. Cosmic Flows 4, released in 2022, pushed the catalogue to over 55,000 galaxy distances. Each successive release improved the mapping of local cosmic flows and refined the characterization of the structures that produced them. The Tully-Fisher relation, which connects a spiral galaxy's rotation speed to its intrinsic brightness and allows distance estimation, is one of the workhorses of these catalogues. It requires measuring the rotation curves of spiral galaxies, typically through 21 centimeter hydrogen line observations, and calibrating the relation using galaxies at known distances. The fundamental plane relation, which does something similar for elliptical galaxies using their velocity dispersion and surface brightness, provides distances to a different class of galaxies. By combining multiple methods and cross-checking them against each other, the Cosmic Flows team has built a picture of local cosmic motion that is more precise and more comprehensive than anything that existed before. This is what understanding our location in the cosmos required. Not a single inspired insight, but thousands of measurements, careful calibrations, decades of instrument development, and the collaborative effort of an international community of researchers. The hole we are in did not reveal itself easily. It revealed itself through the accumulated patience of science. The CMB measurements that gave us the dipole, and from the dipole the direction and speed of our total motion, required satellite missions. The COBE satellite, launched in 1989, first measured the CMB with sufficient precision to clearly detect the dipole. The UMAP satellite, launched in 2001, refined the measurements significantly. The Planck satellite, launched in 2009, provided the most precise CMB map ever made, confirming the dipole direction and allowing cosmologists to measure the Hubble constant from the early universe with unprecedented precision. All of these instruments, all of these survey programs, all of these calculations were aimed at a question that sounds almost philosophical. Where are we in the cosmos? But it is not a philosophical question. It is a physics question, with answers that come from data and that have consequences for the most fundamental measurements in cosmology. The answer we have arrived at is that we are inside a void near the edge of a supercluster, moving through the cosmic microwave background at over 1 million kilometers per hour, being pushed by emptiness and pulled by mass, and doing our measurements of the universe from this specific location. That is a remarkably specific address for a civilization that only left its home planet within living memory, and the work of finding it continues. On a clear night, if you live somewhere dark enough, you can see the Milky Way. It crosses the sky as a band of soft light. The combined glow of hundreds of billions of stars too distant to resolve individually, but close enough in galactic terms to be visible as a collective brightness. It is one of the oldest sights in human experience. Every civilization that looked up saw it. Every astronomer who ever turned a telescope toward it was looking at the inside of the same galaxy. What they did not know, and what we are only beginning to understand fully, is where that galaxy sits in the architecture of the cosmos. The Milky Way is not in the center of the universe. There is no center in the ordinary sense. The universe expands from every point equally, but the Milky Way is also not in a random average location. It is near the edge of a void. It is inside a supercluster. It is participating in a cosmic flow toward a mass concentration hundreds of millions of light years away. It is being pushed by the emptiness behind it and pulled by the density ahead of it. The Milky Way is, in the most literal available sense, not standing still. For all of human history, the sky looked static. The stars appeared fixed in their constellations. The planets moved, which is why the ancients tracked them so carefully, but the fixed stars did not, and the galaxy appeared permanent and unmoving. Human lifetimes are too short to detect the motion of stars in their galactic orbits. The sky 1,000 years ago looked nearly identical to the sky tonight. The sky 10,000 years ago was nearly the same. Even 100,000 years ago, the constellations would have been recognizable to modern eyes. The apparent permanence of the sky was one of the foundations of ancient cosmology. If the stars do not move, the sky is fixed. If the sky is fixed, perhaps it surrounds the Earth like a shell. Perhaps the Earth is the centre of a still universe. The motion that we now know exists, the galactic rotation, the supercluster flows, the crossing of the CMB at over 1 million kilometers per hour, was completely invisible to anyone who looked up before the instruments of the past century were built. But the instruments built in the past century have revealed that the stillness is not real. It is the stillness of a photograph, a frozen moment in a process that is happening at extraordinary speed. The stars are moving, the galaxy is moving, the local group is moving. All of it is flowing through the ancient light of the early universe at velocities that no human sense can detect, but that careful instruments can map with increasing precision. The first person to measure a galaxy's motion through the CMB reference frame using detailed analysis was probably not aware that they were measuring the effect of a void and a supercluster combined. The measurement came before the explanation. The motion was detected before the structure that caused it was fully mapped. Science often works this way. The observation precedes the understanding, sometimes by decades. None of this is visible from the ground on a clear night. The Milky Way looks exactly as it has always looked. Soft, arching, pale, present. The motion is real, over 1 million kilometers per hour, and invisible. The void is real, 150 million light-years across, and invisible. The attractor is real, somewhere toward the constellation Centaurus, and invisible. The entire structure of which we are a part, Laniakea, 520 million light-years across, home to 100,000 galaxies including this one. Visible only to radio telescopes and spectrographs and decades of careful measurement, all of it invisible from the ground. And yet it is there. We are inside it right now, moving through it, being shaped by it, having our measurements subtly biased by it, surrounded by the emptiness of the local void on one side and drawn toward the mass of the great attractor on the other, travelling through the oldest light in the universe at a speed that took decades to measure and centuries of astronomical progress to understand. The Milky Way will cross the void's edge and move further into the surrounding structure over the next billion years. The void will expand behind us as dark energy drives it deeper. The great attractor will pull us and the rest of Laniakea's galaxies toward its centre on a timescale too long for any civilization to observe in a single sitting. The universe will continue doing what it has been doing for 13.8 billion years, expanding, deepening the voids, concentrating the clusters, following the physics of dark matter and dark energy and gravity, without pause and without preference. And somewhere in all of that, on the surface of a small rocky planet orbiting an ordinary star, in an ordinary galaxy near the edge of a void, humans are looking up. The hole around us is not a black hole. It is not a danger. It is not a warning. It is a coordinate. A description of the specific place in the cosmic web that this galaxy and this solar system and this planet and everything on it currently occupies. And it is the place from which all of our observations of the universe have ever been made. We have never observed the cosmos from anywhere else. Every telescope we have ever built, every survey we have ever conducted, every measurement of the Hubble constant we have ever attempted was made from inside this void, near this attractor, from within this supercluster. We have been reading the universe from inside a hole. Now we know the hole is there. The measurements will continue, the surveys will improve. The Hubble tension may eventually be resolved, perhaps partly by accounting for the void, perhaps by new physics, perhaps by both. The map of Laniakea will become more detailed. The local void will be better characterized. the contribution of our specific location to every observation we have ever made will be more precisely understood. But the basic fact will not change. We are inside a void. We are part of a supercluster. We are in motion through the ancient light of the early universe, and all of this has been true since long before any human looked up at the sky and began to wonder about the dark between the stars. You have always been inside this. Now you know it. Good night.